Welcome to today's problem walkthrough. In this session, we'll explore problem number 324, Wiggle Sort 2. This is an exciting problem that challenges our understanding of sorting, reordering, and algorithmic efficiency. Stick around as we dive into the problem statement, break down the approaches, and solve it step by step. Let's get started. In this problem, you are given an integer array called nums, and your task is to reorder it to satisfy a specific condition. The condition is that elements at odd indices, such as index 1, 3, 5, and so on, must be greater than their immediate neighbors at even indices, such as index 0, 2, 4, and so forth. Essentially, the array should form a wiggle-like pattern of less than sign, greater than sign, less than sign, greater than sign when comparing neighboring values. This type of reordering is called a wiggle sort. Importantly, there can be multiple valid ways to reorder the array, and your solution can return any of those that meet the condition. The input consists of the array nums that needs to be rearranged, and the output is the same array modified to satisfy the wiggle sort requirements. Let's look at an example to understand the requirements better. Suppose the input array is nums equals 1, 5, 1, 1, 6, 4. A valid wiggle sort for this array is 1, 6, 1, 5, 1, 4. Here, the reordered array satisfies the condition that each odd-indexed element is greater than its neighbors at even indices. For instance, 1 6 greater than 1 5 greater than 1 4. Notice how the elements at odd indices, like 6 and 5, are greater than their adjacent elements. This example demonstrates that the array does not need to be sorted in ascending or descending order, it only needs to follow the wiggle condition. Here's another example for further clarity. Consider an input array nums equals 1, 3, 2, 2, 3, 1. A valid output for this input is 2, 3, 1, 3, 1, 2. Again, the reordered array meets the wiggle sort condition where odd-indexed elements are greater than their even-indexed neighbors. Specifically, 2 3 greater than 1 3 greater than 1 2. It's important to note that the wiggle pattern is determined only by the relative ordering of the elements, not their absolute values. This means the solution doesn't need to be unique, as long as the condition is satisfied. In terms of constraints, the length of the array can go up to 50,000 elements, and each value in the array is guaranteed to be a non-negative integer no larger than 5,000. The problem guarantees that at least one valid wiggle sort is always possible for the input. For small arrays, such as those with just 1 or 2 elements, no reordering is necessary since the condition is automatically satisfied. On the other hand, for arrays where all elements are the same, such as 2, 2, 2, wiggle sorting isn't possible, but this situation won't occur due to the problem's guarantees. For arrays already sorted in ascending order, a rearrangement is still required to meet the wiggle condition. To solve this problem efficiently, techniques involving sorting and strategic rearrangement can achieve the desired outcome in O(n) or O(n log n) time, depending on the chosen approach. To begin, one of the simplest ways to approach the wiggle sort 2 problem is by using a brute force method that involves sorting the array and then reordering it to meet the wiggle condition. The idea here is straightforward. First, sort the entire array. Once sorted, you split the array into 2 halves, the smaller elements in the left half and the larger elements in the right half. Then, you interleave these 2 halves, placing elements from the smaller half at even indices and elements from the larger half at odd indices. While this approach is intuitive and easy to implement, it has some significant drawbacks. Sorting the array takes O(n log n) time, and creating an auxiliary array for reordering uses O(n) space. More importantly, this method doesn't fully utilize the problem's properties, making it less efficient than other potential strategies. Now, an optimized approach takes the problem to the next level by eliminating the need for sorting and instead leveraging the median of the array. The key insight here is that the median allows us to partition the array into smaller and larger groups, which can then be rearranged to achieve the wiggle order. Specifically, odd indices are assigned the larger elements, while even indices are assigned the smaller ones. To do this efficiently, we first find the median element using a selection algorithm like quick-select, which works in linear time. Then, the array is partitioned into 3 groups, elements smaller than the median, equal to the median, and larger than the median. The final step is to rearrange these groups using a virtual indexing technique. This involves mapping each original index to a new virtual index using the formula 1 plus 2 asterisk I, percent, n1, ensuring that smaller and larger elements alternate as required. This approach achieves linear time complexity, O, n, and works in place, requiring no additional space. While the optimized approach is highly efficient, it does come with added complexity due to the use of virtual indexing and the need to carefully handle the median calculation and partitioning. Despite this, the optimized method was chosen because its linear time complexity and in-place rearrangement make it far superior to the brute force approach, especially for large arrays. The key realization here was that sorting the entire array is unnecessary. By focusing on dividing the array into smaller and larger groups around the median, we can achieve the desired wiggle order much faster. Of course, there are trade-offs to consider. The brute force method is simpler to implement but slower and requires extra space, whereas the optimized approach is faster and more memory efficient but demands careful implementation. Ultimately, the optimized approach stands out as the best choice for scenarios where performance and scalability are critical. To tackle the problem of achieving a wiggle sort pattern where elements alternate between less than and greater than their neighbors, we start with a straightforward brute force approach. First, we validate the input by ensuring we have a valid array of integers with at least 2 elements. If there are fewer than 2 elements, the wiggle sort is trivial. Once the input is confirmed, the next step is to sort the array in ascending order. Sorting helps arrange the smallest elements at the beginning and the largest at the end, which is crucial for reordering later. For example, if the input is 3, 5, 2, 1, 6, 4, sorting would give us 1, 2, 3, 4, 5, 6. This provides a clean starting point for the subsequent steps to achieve the wiggle pattern. After sorting, the elements need to be reordered to achieve the wiggle pattern. This is done using a two-pointer approach. The sorted array is split into 2 halves. The first half contains the smaller elements, while the second half contains the larger ones. For example, with the sorted array 1, 2, 3, 4, 5, 6, the first half would be 1, 2, 3, and the second half 4, 5, 6. These 2 halves are then interleaved, starting with 1 element from the left half, followed by 1 from the right half, and continuing this pattern. If the array length is odd, the last element will naturally come from the right half. For instance, interleaving 1, 2, 3, and 4, 5, 6 results in 1, 4, 2, 5, 3, 6, which satisfies the wiggle condition. It's also important to handle edge cases, such as arrays with only 2 elements, which are simply sorted, or arrays with duplicates, where careful placement ensures the wiggle condition remains intact. The reasoning behind this approach lies in a few key insights. First, sorting the array guarantees that the smallest elements are grouped in the first half and the largest in the second half, which simplifies the process of alternating between them. Second, the two-pointer strategy for reordering is both efficient and intuitive, allowing us to directly interleave elements from the 2 halves. This ensures that the wiggle pattern is maintained throughout. Finally, when handling duplicate values, sorting naturally groups them together. Interleaving the 2 halves prevents consecutive duplicates from violating the wiggle pattern, ensuring that the array still adheres to the required conditions. To implement this approach, we rely on a few essential data structures. The input array itself is either sorted in place or copied to a new array for sorting, which is the most time-intensive operation at O, n log n. Once sorted, we create temporary arrays for the left and right halves of the sorted array. These temporary arrays make the interleaving process straightforward but come at the cost of additional space, specifically O, n. However, it's worth noting that the interleaving step can also be done in place, directly modifying the original array, which eliminates the need for extra space. This trade-off between clarity and efficiency is an important consideration in optimizing the solution. Finally, let's analyze the complexity of this approach. The time complexity is dominated by the sorting step, which takes O, n log n. Splitting the array into 2 halves and then interleaving the elements both run in O, n, so the overall time complexity remains O, n log n. In terms of space complexity, using temporary arrays for the 2 halves results in O, n, additional space. However, if the interleaving is done in place, the space complexity can be reduced to O, 1. This balance between time and space efficiency makes this approach both practical and adaptable, depending on the constraints of the problem. The provided code solves LeetCode problem number 324, Wiggle Sort 2. The goal is to rearrange the elements in the array such that they follow the pattern nums 0, nums 1, nums 2, nums 3, and so forth. Step-by-step explanation. 1. Sorting the input array. The array is sorted in ascending order. This ensures that smaller elements are at the beginning and larger elements are at the end. Sorting simplifies the process of splitting the array into two halves. 2. Finding the middle index. The middle index of the array is computed using n1 //2. This ensures that the first half will have one extra element when the array length is odd. 3. Splitting the array. The sorted array is divided into two parts. The first half, smaller elements, ranges from the start of the array to the middle index, and is reversed to fill the output array from the back. The second half, larger elements, ranges from the middle index plus 1 to the end, and is also reversed for the same reason. 4. Merging into wiggle order. The two halves are merged alternately. The smaller element is added first, followed by a larger element. This alternation continues until all elements are merged into the final wiggle order. 5. Edge cases. The algorithm handles arrays of odd and even lengths seamlessly due to the careful division of the array into reversed halves. The alternation ensures the wiggle condition is met. This approach uses O, n log n, time for sorting and O, n, space for the reversed halves. The implementation is both efficient and easy to understand. Here, we start by sorting the input array. Sorting ensures that the numbers are in ascending order, which is essential for constructing the wiggle pattern. Next, we calculate the middle index of the sorted array. This index helps us split the array into two parts, the smaller elements in one half and the larger elements in the other half. We then create two subarrays using arrays.copyOfRange. The smaller half contains elements from the start of the array up to the middle index, while the larger half contains the rest of the elements. To prepare for the wiggle sort, both halves are reversed. This reversal is important because we'll be filling the wiggle order from the back of each half. Finally, we interleave the two halves into the original array. We iterate through the smaller half and alternate between placing an element from the smaller half and the larger half. If the larger half has extra elements, they are seamlessly added as we continue the merging process. To complete the implementation, we define a helper method called reverse. This method takes an array and reverses its elements in place. It uses two pointers, one starting at the leftmost element and the other at the rightmost. The pointers move toward each other, swapping elements at each step. This continues until the pointers meet or cross, ensuring the entire array is reversed. The reverse method is crucial for rearranging the two halves of the sorted array before they are merged in wiggle order. By reversing each half, we ensure that the smallest numbers alternate with the largest numbers during the merge, achieving the desired wiggle pattern. To solve wiggle sort 2, let's start with the first example where nums equals 1, 5, 1, 1, 6, 4. The first step is to sort the input array in ascending order. Once sorted, nums becomes 1, 1, 1, 4, 5, 6. Next, we calculate the middle index. Since the length of the array, n, is 6, the middle index is calculated as n1 divided by 2, which equals 2. Now, we split the sorted array into two halves. The smaller half includes elements from the start up to and including the middle index, but it's reversed to order elements from largest to smallest. This gives us the smaller half as 1, 1, 1. For the larger half, we take the elements after the middle index and reverse them, resulting in 6, 5, 4. Now that we have the smaller and larger halves, the next step is to merge them together in wiggle order. We start with an empty nums array and interleave elements from smaller underscore half and larger underscore half. First, we add the first element of smaller underscore half, which is 1, so nums becomes 1. Then, we add the first element of larger underscore half, which is 6, updating nums to 1, 6. Next, we take the second element of smaller underscore half, another 1, and nums becomes 1, 6, 1. We continue by adding the second element of larger underscore half, which is 5, making nums 1, 6, 1, 5. Finally, we add the last element of smaller underscore half, which is yet another 1, resulting in 1, 6, 1, 5, 1. To complete the merge, we add the final remaining element from larger underscore half, which is 4. This gives us the final nums array as 1, 6, 1, 5, 1, 4. The wiggle sort is complete for this example. Let's move on to a second example where nums equals 4, 5, 5, 6. As before, we start by sorting the input array in ascending order. Once sorted, nums becomes 4, 5, 5, 6. Then, we calculate the middle index. Since the length of the array is 4, the middle index is n1 divided by 2, which equals 1. With the middle index determined, we split the sorted array into two halves. The smaller half includes the first two elements, reversed, which gives us 5, 4. The larger half contains the last two elements, also reversed, resulting in 6, 5. Now, we merge these halves together in wiggle order. Starting with an empty nums array, we add the first element of smaller underscore half, which is 5, so nums becomes 5. Next, we add the first element of larger underscore half, which is 6, making nums 5, 6. Then, we take the second element of smaller underscore half, which is 4, and nums becomes 5, 6, 4. Finally, we add the last element of larger underscore half, which is 5, resulting in 5, 6, 4, 5. This is the final wiggle sorted array for the second example. Let's now consider a third example where nums equals 1, 3, 2, 2, 3, 1. For this third example, we start by sorting the input array in ascending order. After sorting, nums becomes 1, 1, 2, 2, 3, 3. Next, we calculate the middle index. Since the length of nums is 6, the middle index is n1 divided by 2, which equals 2. Now, we split the sorted array into two halves. The smaller half consists of the first three elements, reversed, which gives us 2, 2, 1. The larger half contains the last three elements, also reversed, resulting in 3, 3, 1. Now, we merge the two halves into a wiggle order. Starting with an empty nums array, we add the first element of smaller underscore half, which is 2, making nums 2. Then, we add the first element of larger underscore half, which is 3, so nums becomes 2, 3. Next, we take the second element of smaller underscore half, which is 2, and nums becomes 2, 3, 2. Adding the second element of larger underscore half, which is 3, updates nums to 2, 3, 2, 3. Finally, we add the last element of smaller underscore half, which is 1, resulting in 2, 3, 2, 3, 1. To complete the merge, we add the final remaining element from larger underscore half, which is 1. This gives us the final nums array as 2, 3, 2, 3, 1, 1. With this, the wiggle sort is complete for the third example. By following these steps, we can ensure that the array is rearranged into the desired wiggle pattern where adjacent values alternately increase and decrease. To analyze the time complexity of the algorithm, we break it down into key steps. First, sorting the array using Python's built-in timsort algorithm takes n log n, as this is the complexity for sorting an array of size n. Next, finding the middle index involves a simple calculation, which is an O1 operation. After that, we split the array into two halves. Slicing the array to create smaller underscore half and larger underscore half involves iterating through the array, which takes n. Additionally, reversing each half also takes n in total, as the sum of the sizes of the two halves is equal to n. These steps set the foundation for understanding the overall time complexity of the algorithm. In the next step, we merge the two halves to achieve the wiggle order. Clearing the nums array is an O1 operation. Then, the for loop iterates approximately n/2 times, appending elements from smaller underscore half and larger underscore half back into nums. Since each append operation is done in constant time, the total time taken for this step is n. When combining all the steps, the sorting operation remains the dominant factor with a complexity of n log n, while all other steps contribute linear or constant time. Therefore, the total time complexity for this algorithm is n log n. Now let's examine the space complexity. The input array nums is modified in place, so no additional space is required for the input beyond its original storage. However, when we split the array into smaller _half and larger _half, we create two new lists that together hold all n elements of the original array, requiring n additional space. Temporary variables like in, mid, and the loop variable I only consume constant space, which is 1. These components collectively define the space usage of the algorithm. Summing up the space requirements, the creation of the two halves dominates the additional space usage, contributing n to the overall space complexity. Therefore, the total space complexity of the algorithm is n. When we compare this solution to a brute force approach, the difference is stark. A naive method might involve generating all permutations of the array, which has a time complexity of n, and is computationally infeasible for large inputs. By contrast, the current solution efficiently leverages sorting and splitting to achieve the desired wiggle order in n log n time, making it far more practical. Finally, while this solution uses n extra space for the two halves, it is worth noting that an even more optimized approach could potentially achieve the same result using in-place modifications. This would reduce space usage to 1, but would require careful index manipulation, which adds complexity to the implementation. To summarize, the optimized solution runs in n log n time, dominated by the sorting step, and uses n additional space for the two halves. Compared to the brute force approach, this algorithm is significantly faster and more practical, especially for handling larger inputs. When solving wiggle sort 2, there are some common mistakes to watch out for. First, it's important to correctly interpret the wiggle sort conditions. The required order is nums 0, nums 1, nums 2, nums 3, not the reverse. Misunderstanding this can lead to completely incorrect results. Another frequent issue is relying on a brute force sorting approach without validating the output. Simply sorting and alternating elements might seem quick, but it often fails when duplicate values are present, leading to invalid wiggle patterns. Additionally, edge cases like arrays with fewer than 3 elements or arrays with all identical values can trip you up if you don't handle them explicitly. Lastly, adding unnecessary complexity by using data structures like heaps or auxiliary arrays may seem like a good idea, but it bloats the space complexity unnecessarily. A more efficient in-place solution is usually sufficient and preferred. Another pitfall to avoid is neglecting time complexity. Solutions with n² complexity, like those involving nested loops or inefficient reordering, are too slow for large arrays and won't perform well in interviews. Now, when you're tackling wiggle sort in an interview, there are a few key insights to keep in mind. First, these problems often revolve around recognizing a simple pattern, and in many cases, you can solve them with in-place swaps rather than overcomplicating things with extra structures. The central idea is to focus on alternating comparisons, and, rather than getting bogged down by absolute values. For optimal strategies, an n greedy approach or an n log n sorting-based approach typically works well. It's also crucial to communicate clearly how your solution handles duplicates and edge cases, as this is often a point interviewers will probe to assess the robustness of your approach. Remember to discuss the trade-offs between time and space efficiency, choosing between in-place manipulation for O1 space versus auxiliary data structures for O(n) space. Wiggle sort problems are closely related to a few other LeetCode challenges that can help you build your understanding. For example, LeetCode 324, Wiggle Sort 2, is a direct counterpart with additional constraints, particularly involving median values. LeetCode 376, Wiggle Subsequence, shifts the focus to identifying wiggle patterns within subsequences, which requires a slightly different mindset. LeetCode 31, Next Permutation, shares the concept of reordering elements to meet specific conditions, and learning this can help you better understand how to manipulate arrays efficiently. Lastly, LeetCode 41, First Missing Positive, emphasizes in-place manipulation under constraints, which is another valuable skill to develop for problems like wiggle sort. Studying these related problems will deepen your problem-solving toolkit and help you recognize common patterns and strategies. There are several alternative approaches you can consider for solving wiggle sort 2, each with its own trade-offs. The greedy in-place approach is one of the simplest and most efficient methods. Here, you iterate through the array and swap adjacent elements if they violate the wiggle condition. This method operates in n time with O1 space, but it requires careful attention to edge cases to work correctly. Another option is the sorting-based approach. Here, you sort the array and then reorder elements by alternating between the left and right halves. While this method is easier to implement, it has a time complexity of O(n) log n, and a space complexity of O(n), making it less efficient in terms of memory. Finally, the two-pointer approach involves partitioning the array into smaller and larger halves and then merging them in a wiggle order. This method strikes a balance with O(n) log n, time and O(1) space complexity, but it requires precise pointer management to avoid mistakes. Each of these approaches has its merits, so the best choice depends on the specific constraints and goals of the problem you're solving. Great work! To recap, we tackled the wiggle sort 2 problem, reviewed approaches, and focused on optimizing the solution. Keep practicing problems like this to strengthen your algorithmic thinking. Thank you for watching, and be sure to stay tuned for more tutorials. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!